All right, welcome back, everybody. So in the last video, I cut off our examples of first-order linear equation solutions little soon there, but what I wanted to do here is make sure that we went through a solution at kind of a glacial pace, just to make sure that we're understanding how this works exactly. So here's another example that's a little bit different from the other two that we did in the previous video. And this is x times dy dx plus 2y equals 4x squared. And you know what, just for the hell of it, I feel like putting in an initial condition because I'm feeling particularly cheeky. And what do I mean by that? You'll see very shortly. So I'm going to use y of 0 equals 3. Why not? So let's have a look here. Let's put this guy into prime notation and then ask ourselves, is this in standard form? Well, no, because there's an x sitting in front of the y prime. So I have to make sure I divide the equation through by the x that's sitting in front of the y prime. And I wind up with this as my standard form. Great. And we identify, here's p of x, and here's q of x. Excellent. Pun certainly intended. Anyway, so the integrating factor here that we're going to need, mu of x, is given by e to the integral of p of x dx. And in this case, this will be the integral of 2 over x dx. And scholars of Calc 2 will be able to tell me that the antiderivative for a reciprocal, the 1 over x function, yes, indeed, this is the natural log of the absolute value of x. If you didn't remember the absolute value, now you remember. If there's no domain specified on that integral, then we need to make sure we're including all non-zero x's as part of that antiderivative, hence the absolute value. But in this case, we're a little, well, we can't really do too much with this guy, but we can actually simplify it a little bit, where we really don't even need to worry about that absolute value sign at all because we're squaring the result. So e to the natural log here shows that the integrating factor is actually a polynomial. Wonderful. So now comes the fun part where we realize, oh, wait a minute, x squared times y prime plus 2x times y is equal to 4x and then times the integrating factor on the right-hand side. Okay, so turns out that this equation was just a multiple of x away from the correct thing from the beginning. But we didn't recognize it because we're not necessarily, maybe we didn't necessarily recognize it because we are just learning this. This is the first time we see it. But notice that if you can identify the product rule here without having to use your integrating factor, first of all, my hat's off to you. Those are really hard to see just by looking at the equation. But second of all, it's like, oh, okay, they'll become second nature and you'll be able to recognize them in certain cases very readily. But anyway, we wind up with this equation, and we see that this is exactly what happens if you differentiate x squared times y on the left-hand side. So I haven't done any calculus in this step. I'm just saying, here's what the product rule looks like. So the question now, why did I write that as that? Why not just write it as a cube? There we go. Now I can integrate both sides, and I'll wind up with x squared times y on the left because I'm integrating a derivative. And on the right-hand side, I notice the power rule that shows up. Wonderful, there is a power rule here. And then I say, okay, great. I can go ahead and just divide through by an x squared and I'm done, correct? Well, sure, here's my general solution. But there's a subtlety here. If c is equal to 0, then that means I'm not allowed to use x equals 0 as any part of my solution. So, let's think about that. That means that my solutions are separated by what happens when c equals 0. So I'm going to go ahead and mark that. Here's the parabola y equals x squared. Oh, look at that. That's pretty darn good for for freehanding. So this is the c equals 0 solution. Now, the other half of these, if c is a negative number, the only way that I'm going to, I'm going to be underneath the parabola here, which means I look something like that on the left, and still under the parabola on the right. So this would be for something like c equals -1. Or I could also have something that looks like this for an even smaller value of c, so maybe something like c equals -10. But then I also get solutions above the parabola, and these would be for the positive c values, perhaps. So the real thing to take into consideration here is that I'm not allowed to use x equals 0, and my solutions actually reflect that. They say that I definitely cannot use any initial conditions that live on the x-axis unless I am this c equals 0 solution, which does not satisfy my initial condition, right? So y equals x squared would imply, not to the 7th, squared, that y of 0 would have to equal 0. So the only initial condition that works for x equals 0 is if I am actually sitting on this little parabola, this red parabola through the origin. So I do have to be very careful in how I construct my initial conditions in general. Not all initial conditions will have solutions. So this goes back to our original goals for ODEs in general, or differential equations in general, about existence of solutions. This particular initial value problem does not have a solution, right? And I should put that in red. Solution does not exist. Okay, and that's a huge deal. Not every differential equation with an initial condition has a solution. And that shouldn't be too crazy, right? We've seen algebraic equations that don't have real solutions. So sure, why not have a differential equation that doesn't have a real solution? It doesn't even have a complex solution for that matter. But the point is that we do have to be careful with these initial conditions, and they don't always have to sit on 0. So in this case, if I change my initial condition so that it is a 1 instead, let's have a look. This will actually now have a solution. Let's kill off that little bit there. So if I use x equals 1 and y equals 3, that means, oh shoot, no, come back. That means, sure, I should probably be sitting on a function or a branch of the function that looks like this. And yeah, let's try it. Y of 1 is equal to 1 squared plus c over 1 squared by my general solution. And y of 1 would have to be a 3. So that means 3 is equal to 1 plus c, so that c is equal to 2. And that would mean that my solution is x squared plus 2 over x squared. And now, here's the tricky part. What's the solution space for this function? Well, this guy for x greater than 0, right? That's the only function that it could be on the right-hand side of 0, right? That's the only guy that satisfies this initial condition of y of 1 equals 3. So what about the left-hand side? Well, a lot of the time we're just going to go ahead and say that our solution has to be defined on a single contiguous interval. And in this case, that solution space would be from the open interval from 0 to infinity. So this really would be the end of the line. That's what the function is. There is one thing that's nailed down. But if we are going to allow there to be a second half of this equation, or a second half of this solution, then any one of these other left-hand sides would satisfy, except for the red c equals 0 solution. Any other left-hand side of the equation would work. The reason why it doesn't work for red is because the red solution is actually continuous, and we need this guy to be discontinuous at 0 to match the fact that this guy down here blows up at 0. So what we'd ideally like to see happen here is that we get any solution to the differential equation on the left-hand side except for the continuous one, but we definitely nailed down what this guy looks like on the right. So honestly, this would be a complete solution if I wrote it as what I had for my right-hand side. So this is the piece that satisfies the initial condition, and then this guy is allowed to do whatever he wants for x less than 0, so long as it still satisfies the differential equation, but there is no initial condition on that side of the equation, so nothing has been pinned down, and I'm allowed to use this as a general solution. But to match our theory, we really want to make sure that this is the solution, and we include this as our solution space. Okay, and we'll see exactly why. We want to make sure there is exactly one solution to each initial value problem that we encounter. And this thing in the box doesn't satisfy that bill. So we usually reject this as a complete answer, even though it's totally valid, and instead use this as our unique solution to the initial value problem. Cool, so there is a subtlety there, and I wanted to make sure we understood it. That this is actually very, very subtle, and we leave the subtleties mostly to the pure mathematicians. But the best applied mathematicians know their theory very, very well. So you now know the subtleties, a subtlety to some of the theory, and hopefully you can use that in the future. And especially in the following section that we're going to start tackling in the next video, we're going to start talking about separable equations.